Would you like to get the chance to win a ROS developer's shirt and practice some ROS along the way? Then stay with me. This video is for you. Hello ROS developers and welcome to a new video of the ROS Mini Challenge, solving the ROS Mini Challenge video series. Today we are going to be solving the ROS Mini Challenge number 9, as you can see here. And for those who don't know it, this ROS Mini Challenge is a challenge brought to you by Deconstruct, where you are presented with a ROS-related problem, challenge, that needs to be solved by you. And the fastest one to solve it and to share their correct solution, of course, with us, will get an amazing prize, which is a ROS Developers t-shirt. So yeah, let's go for it. So let's start solving this ROS Mini Challenge number 9, and for that, the first thing we'll need to do is to click here on the link of the challenge, which basically will create a copy of this challenge into our workspace, into our ROS.ds workspace. You'll see right here. So here we have our copy of this challenge. And in order to open it, you just have to click here and open ROSject, and this will start loading the environment, loading your ROSject. There we go. And meanwhile, it loads, which shouldn't take too much time. I'm going to explain a couple of things. So first of all, as you can see this challenge here, we can have a preview here of the notebook without opening it. And as you can see here, we have an intermediate level challenge. So basically you have 3 different levels: the beginner, the intermediate, and the advanced level. So this is the middle one. And in this one, for instance, you will have to face a problem which is related to the robot localization package, as it is explained here. And for instance, here we have our ROS courses, our Robotics Academy, in case you don't know it, where we have many featured courses, many different courses of many different ROS topics. So here you can see the ROS basics, both in Python and C++. We have free courses as well for Python and Linux, which will help you send the base knowledge you need in order to learn ROS. Many different courses. We have a brand new using NVIDIA Jetson Nano with ROS course, which is being a success so far. So I really encourage you to have a look at it. It's super interesting and super useful. Also ROS manipulation course, for instance, which we have, by the way, updated this week with some new content related to MoveIt, with the updated version of MoveIt, also a new grasping chapter, super interesting. And for instance, here we have this course, which is named Fuse Sensor Data to Improve Localization. In this case, in this course, basically we are explaining how to configure this robot localization package, yeah? So in order to solve this challenge, the most useful course would be this one, yeah? With this course, if you complete this course, you would be completely able to solve this challenge in a quite easy way, I should say. So yeah, I really encourage you to have a look at this at our academy, have a look at the different courses we have, and if you are interested in any specific topic, just go for it, yeah? So yeah, let's close all this and let's come here to the challenge, which here we have it already loaded. Excellent. And as always, the first thing we are going to do in order to solve the challenge is to start following the instructions here stated in the notebook. And the first thing is to start the simulation. So for this, we are going to come here to the simulations menu, choose launch file, and we are going to select this one, the ROSject of the week 9 launch file. So let's come here, choose launch file, and select the ROSject of the week 9 launch file. Excellent. So yeah, if everything goes right, we should get something like this here in the gazebo simulation window, with a Summit XR robot loaded here in a kind of office environment, yeah? And right below here we have basically the instructions for the problem to solve. And here it starts saying that this project contains one package inside the Catkin workspace, which is named ROSject of the week 9 underscore package. So let's come check this real quick by opening here the IDE, where we are going to be able to visualize all the workspaces and all the files we have there. So let's make this bigger, and here inside the Catkin workspace, in the source folder, we can see this ROSject of the week 9 package, yeah? and it says this package contains a launch file and a configuration file. So here we have the configuration file and here we have the launch file. Okay, so far so good. Which are used to start an AKF localization node. Yeah, this AKF goes for Extended Kalman Filter. This node is provided by the robot localization package, and its main purpose is to fuse different sensor data inputs in order to improve the localization of our robot. In our case, we are going to use odometry data, which has been tweaked by us, with IMU data, which is correct. So the main purpose of this challenge is to improve the Summit Excel odometry data since the initial one is a little bit distorted. Alright, then here we have also the simulation, which has been properly loaded. Let me refresh this here so that the rendering ends correctly. There we go. So here I have our Summit Excel robot in the office environment. Let me modify here a little bit the view. There we have it. Excellent. Then in order to test that it works as expected, all you have to do is the following. So first of all, we need to know the odometry topics. For this, we can use the following command. Okay, so let's start opening a shell and start executing all these commands. So let me copy and paste right here this command, and this command will give us the following topics. So yeah, here we can see that it gives two topics, the noisy odometry and the Robotnik base control odom. Yeah, so basically this is the correct odometry. Yes, this is the odometry which is right here for the Summit Excel robot, and this noisy odom, is the one which is tweaked by us. Yeah, so for this challenge we are going to use the noisy odom topic, which basically is the original odometry data with some extra noise added to it. And we can have a look to this current odometry using the Pervis. Okay, so let's start an Pervis window right here. ROS run Pervis. There we go. Yeah, so here we are going to be able to visualize this noisy odometry, which is, as I've said, is tweaked by us. Specifically, we have basically added some noise to the E-axis, yeah, to the data of the position of the robot in the E-axis. So we are going to see it right now in Pervis. So let's open a graphical tools window here, which will allow us to visualize Pervis. I'm also moving it to a new window so that I can visualize it better. There we go. So here we have Pervis. Let me configure, set up everything correctly here. I'm going to set here the base link frame. Excellent. I'm going to add as well a robot model display so that I can visualize the Summit Excel robot. And then I'm going to add as well an odometry display, which I should have here. Here I have it. Excellent. And here I'm going to select the noisy odom, which is the tweaked one, the one we want to use. Okay, and here we can see the covariance growing really fast, so let me deactivate it. And great, so here I have the noisy odometry, which as you can see, it's moving here around the E-axis. Yeah, it has noise here around the E-axis. So yeah, basically we need, the purpose of this is to improve this localization so that we have a fixed and stable odometry data. Yeah. Excellent, so let's continue here, and so now let's start our node in order to correct the odometry readings with the following command. Alright, so now we are going to start our AKF localization node with this command, which should improve the localization. So let me start it right here in a different shell. There we go. Then this command will generate a new odometry topic named Odometry Filtered, which will contain the resulting odometry data, fusing the noisy odom data with the IMU data. Alright, then if you visualize this new odometry, you will get something like this. So as you can see here, we have the tweaked odometry, which is going all around the y-axis, and this is the odometry filtered, the corrected one, which as you can see, it's stable. Yeah, it's not going around here. So it's fixed, it's stable. So this is basically what we want to achieve, yeah? So for this, let me modify the displays as we have them here. So I'm going to make these arrows a little bit shorter here, half, for instance, and I'm going to change the color as well, so that I can differentiate them. I'm going to change them to blue. There we have it. Here we have the odometry going all around the y-axis. Let me get here a bit closer. There we go. All right. And now, okay, so this command, as it's stated here in the notebook, should have generated this new odometry filter topic. So let's have a look. Here we will need a new shell. There we go. And let's filter one more time here the odometry topic. So ROS topic list grep odom. Let's see if we have this new filter topic. Yeah, so here we have it, the odometry filter topic. Okay, so what we are going to do now is to add a new display. Let me minimize this one. And I'm going to add a new odometry display here. And this one I'm going to set it to odometry filtered. So let's set this to odometry filtered. There we go. And okay, so we are getting nothing. Alright, so as you can see here from the notebook, we should get here the stable arrow for the odometry filtered topic, which is the corrected odometry, but instead we are getting nothing in our case. Alright, so this is telling us that something is wrong, which is quite normal, because otherwise what would be the challenge, yeah, if everything was working? Okay, so now we see that this is not working properly, so now we need to figure out what's going on here, yeah? So let's do this right now. So for this I'm going to come back here to the IDE, which I should have somewhere here. Here I have it. And basically here we have two files, yeah? So we have the launch file, which, as you can see, we are launching here the AKF localization node from the robot localization package, and we are basically loading here the parameters file, here from the config folder, the AKF localization.yam file, which we have right here, yeah? So nothing strange, nothing wrong here in the launch file. So let me close here. So we are going to focus on this configuration file, the AKF localization.yam file. Then now here we have many parameters, many different things, which we are not going to enter into much detail now, because it would be a very large video. As I've said before, if you want to learn more about these parameters, what they mean, how they work, how you should configure them, you can learn all this here in our course, in our Ignite Academy course, this one specifically, the Fuse sensor data to improve localization, yeah? So here you will get all the necessary information about all the different parameters here, how to configure them, etc, etc, yeah? But for now we are going to go straight to the point. So basically we are going to focus on two things. First of all, here we have the frame definition. So we are defining two frames, the odometry frame and the baseline frame, and finally a world frame, yeah, which in this case it's the same as the odometry frame, because we do not have any external localization system, yeah? If we had an external localization system, then this should be probably changed to the map frame, yeah? But however, I'm not going to enter into details. So basically you have this odometry frame and the baseline frame, yeah? So first thing we are going to make sure is that this is correct. How we can do this? Okay, so in my case, what I'm going to do is to basically come here and generate a TF tree, yeah? So for this, I'm going to execute this command, run TF view frames. And this command is basically going to generate here in the Catkin workspace source folder, is going to generate a PDF file which will contain the full frames tree of this simulation, of my simulation, with all the connections and the names of the frames and everything. You are going to see it right now, yeah? So yeah, so you will see now that here in the source folder, two files are going to be generated. One named frames.gv, you have it here, and the other one it's named frames.pdf. So I'm going to download this one here to my computer. I'm going to open it. Let me close here, and basically here you have the full frame tree of my simulation, yeah, with all the frames. So for instance, here we have the front right wheel, front left wheel, back right wheel, back left wheel, the EMU, here you have the GPS, the RGBD camera, etc, etc. yeah? And here at the top, we have 3. One is the odometry frame, which as you can see here, it's named Summit XL A Odom, yeah? Then this one is connected to the Summit XL A base footprint, which is connected to the Summit XL A base link. Yeah, so basically here we have the names of these frames. So the base link frame is named Summit XL A base link, and the odometry frame is named Summit XL A Odom. Yeah? So now we have the names, and we can clearly see that here they are wrong. Yeah? So let's quickly modify this. So here we should add a Summit XL A Odom, and the same for the base link down here, Summit XL A base link, and as well we should modify it here, yeah, because it's the odometry frame. So okay, we now have them right, Summit XL A Odom and Summit XL base link, as it is stated here. Excellent. So we have solved this. Let's save our file and let's try to run again our localization node to see if the problems have been solved or if we have to check on anything else. Alright, so let's see what we get now here. Still loading. Let me, by the way, deactivate here Pervis, so that the odometry, for instance, so that it's not consuming resources, not this one, but this one. Yeah, there we go. I'm going to close as well here. Great. So let's come back here and alright, so okay, so here we have our localization node launched again. So let's set up the noisy odometry, and to compare it, let's also activate. Alright, so basically we have here the odometry filtered, which is being the same, yes, as the noisy odom. So this is still not right, yes, because we should have, as we can see here on the notebook, we should have one stable odometry, yes, and we are not having it. So we are having noise as well in the y-axis here. Alright, so still not right. So we can see the odometry filtered, so it's something, but it's not correct, yeah? So if this is not correct, probably the error should be here, yes, in the config, in this matrix here, yes? Then I should focus here, because as you can see here, the name of the topic is right, so we are getting it from the noisy odom, which is the one which is tweaked, but it's not correct, yeah? So probably I know that the error should be here in the matrix. So now what I'm going to focus is on this matrix. So if you don't know, basically here you can see that we have different rows. The first row, it goes for the XYZ position, yes. The second one goes for the roll pitch yaw, so the orientation of the robot. Then this is the differential value of the position, so the linear velocity. This is the differential value of the orientation, so the angular velocity. And this final row is the linear acceleration, yes? Then here, basically, as you can see, we are inputting the velocities in x and y, and here we are inputting the angular velocity in z, yeah? So the angular velocity in z and the linear velocity in x make totally sense, because our robot is controlled, in this case, with a differential drive control, which basically only allows movement in the linear x velocity and in the angular z velocity, yeah? So it makes perfect sense here that we are inputting this. And the linear velocity in y doesn't make much sense, but for convenience we need to, well, it's not necessary, but it's good to input it as well to the input, although it's going to be 0 values, yeah? But, well, yeah, all of this, as I've said, I'm not going to enter into details, so you can find all this information in our course or in the official documentation of this package, probably. So yeah, what I'm going to have a look here, as well we are inputting here the Z orientation, yes? But here, we can see that we are as well inputting the X and Y position, yes? And this doesn't seem right. First of all, because we are already inputting here the velocities in X and Y, which basically, with these values, we already have these ones, yes? Because, basically, this is the differential value of this, yes? But furthermore, my original odometry is being tweaked here in the position, specifically in the Y position. I'm adding noise to my original odometry. So basically, why would I want to add this value if I am basically tweaking it here? Yes? So if I directly input this into the Kalman filter, I'm inputting a value which I know that I am tweaking. Yes? So let me come here and set this to false. And as well, I'm going to set the X position to false. Yes? So now, alright, so we have all the positions to false, and we are only getting here the values from the velocities. Yeah? Alright, so let me save this, and let me try this again without inputting the X and Y positions to the Kalman filter. So let me start one more time the localization node. Let me deactivate everything again here. Alright, and let me real quick here make sure when the odometry filter topic is available. Let's see, so not yet. We have only the noisy odom and the correct odometry here, but we need to have this odometry filter topic. Okay, so I think now it has been, everything started here, so we should have it. Yeah, here I have it, the odometry filtered. And now I'm going to visualize the noisy odometry, the one which is wrong. Here we have it with all these dispersed arrows. And I'm going to activate now the odometry filter topic, which now I have it correct. So I have it stable here at the center of the robot in the right orientation, yes? Without moving around. Excellent. So we have basically solved this challenge. We have corrected the odometry of the robot using the IMU data. And yeah, we have solved the challenge. So awesome. And yeah, that's all for the video of today. So I hope you've enjoyed this video. You've learned something new, of course. And I will see you in next week's video. So meanwhile, keep pushing your ROS learning, and goodbye.